So let's prove the triangular inequality for induced norm by the inner product. Triangular inequality for induced norm. When I'm saying this induced norm, so I'm saying this is the norm induced by inner product, right? I'll more precisely write it. So we know that if E is a vector space, let's say E is a vector space, so if E is a vector space with this inner product, so suppose this E is an inner product space. Now what I want to say is this. So we know that if E is an inner product space, then on it I can define this norm of any element F from this E. I can define this norm by this inner product, right? So now I will do what? I'll prove that this norm, under this norm, triangular inequality holds. In other words, F plus G is less than equal to the norm of F plus norm of G. So norm of sum is less than equal to sum of the norms of the elements from the vector space or the inner product space. But one more thing that I will assume here is the field here is the k, which can be either real numbers or k is a complex numbers. So let's say it's a complex field. Okay, so let's work with it. So as we know that my norm of f plus g squared is given by f plus g inner product of f plus g with f plus g inner product. So now you can use the suscallarity of the inner product space, and you will applying this, so you can write this f with f inner product, and then f with g, and then inner product of g with f, and then finally you can write the inner product of g with g, right? So now you can see that this f, when it is taken it is understood as an inner product with itself, then it becomes the norm of f squared plus, so this is f comma g plus, now I can write this as inner product of f and g conjugate, and this guy is the norm of g squared. So this norm is under E, right? Now whatever this is and whatever this is, these both elements are from the complex numbers. So you can say that these are complex numbers. So if this is z and this is z bar, then you can recall that z plus z bar is equal to 2 times the real part of z, right? So in other words, I can now write this is the norm of f squared plus this is 2 times real part of inner product of f with g, right, plus the norm of g. But you can also see now one more thing that you can recall is so let me write it in this way. We know that x square plus y square is always greater than equal to x square. So this is nothing but the norm of z square, which is greater than equal to x square. So for the complex number z, so from here you can see that the absolute value of our complex number is greater than equal to this x is a real part of z, so I can say this way. So the absolute of the complex number, in other words this complex number, if I take its absolute, then it is going to be greater than this real part. So I can write this as 2 times the absolute of the inner product fg plus this g squared, right? And now you can use the Cauchy-Schwarz inequality So norm of f squared plus 2 times norm of f and then norm of g plus norm of g squared, and then you can write this as the norm of f plus norm of g, all of this squared. It is greater than equal to f plus g norm squared. So from here you can directly deduce this triangular inequality, right? So we use the Cauchy-Schwarz inequality.